Thanks everyone for joining us today. This is our 13th Graph Guru episode, and we're super excited that you're here with us and learning about the most recent graph solutions with TigerGraph. Today's presentation is on visualizing Bitcoin blockchain with TigerGraph. A couple of housekeeping items before we get started. First, all attendees, you're muted by default, but you can talk to us via chat in Zoom. And if you have questions, you can submit through the chat and the Q&A box, and we'll address them at the end of the webinar. And the session is being recorded. After the webinar, we will provide a link to you with the recorded presentation. I just want to remind everyone that the developer edition is available, and the version 2.3 was already released, and you can try download the Docker version and VirtualBox version of TigerGraph with the developer edition and run on your laptop. So get to the link and download the new 2.3 edition. All right. Let me introduce today's guru. I am Emma Liu. I'm a senior product manager at TigerGraph. And I'm working on areas in cloud services, containers and Kubernetes, and enterprise infrastructure, monitoring and management, as well as ecosystem connectors. If you have questions regarding these areas, let me know and provide us feedback. And previously, I've worked at Oracle and MarkLogic as product manager. And joining me today, our main presenter today is Sai Pusapati. And Sai is a sophomore from MIT. And he is majoring in computer science and engineering. And he has done many projects, including topics in machine learning, parallel processing, and big data. And Sai was an extern at TigerGraph in winter 2019. And he also worked as an intern previously at Visa in the summer of 2018. All right, our agenda today is first, we're going to, Sai is going to show you how to load the Bitcoin dataset into TigerGraph. And then also demo the Bitcoin blockchain in TigerGraph. And I'm going to talk about potential future work using the Kafka loader with 2.3 TigerGraph for the blockchain live data. Just briefly on what is MIT Externship. MIT Externship is a 4-week internship during winter independent activities period, IAP. So this year it's in January, and every year it's pretty much in January. And basically it's the MIT alumni hosting the current MIT students to do projects in their current work. And it's a very good opportunity for the current MIT students to get firsthand experiences at actual workplace. And I was fortunate enough that I was able to host the MIT Externship this January, and also working with the bright MIT undergrad students. And Sai was here in January 2019, and he joined us for 4 weeks, and he learned how to use TigerGraph, installing it and writing GSQL very, very fast. We were really impressed, and he was also helping us to do the blockchain solutions. And he did a lot of the pre-processing from the blockchain raw data to the CSV data, and then also using our loader to load into TigerGraph. In addition to that, he wrote some queries and brought new knowledge about blockchain to the entire engineering team. So without further ado, I'm going to hand it over to Sai and talking about visualizing the Bitcoin blockchain with TigerGraph. All right. Sai, you can take over.
Hi, guys. So glad to be here. So to get started, I wanted to give a brief background on blockchain, specifically in context of payments, as that's the most prominent way that we see it today. And to also start, I wanted to talk about how we currently view transactions. So let's say I owe someone $5. The way I would solve this is by handing them, the recipient, a $5 bill. While this may seem like a simple transaction, a lot of significant things just happened. The recipient was able to acknowledge my presence. I was able to acknowledge the recipient's presence. And by the physical form of the cash allows the recipient to immediately take it, and he's able to verify it on his end. Along with this, I am, as the payer, unable to double spend unless I somehow steal the money back and pay it on something else. So this is what we call a truly trustless system. At no point in this transaction did either party, as me as the payer or the recipient, have to place their trust into anything. Both parties could verify pretty much everything in the transaction. But obviously, since current day transactions probably deal with larger transactions than $5 and recipients aren't nearby where you can hand them physical cash, we now place our faith in a sort of central authority for verification of this transaction. And this comes in the form of banks or companies like Visa and PayPal. And these systems do require trust. We put our faith in that these central authorities will verify these transactions properly. Blockchain rejects this idea of a central authority and wants to go back towards a trustless system. But if someone tells you that blockchain is trustless, that is not necessarily accurate. Blockchain can be better described as distributed trust, where the trust is distributed over a series of entities. And in this case, it is a network of computers. And each computer uses public-private key cryptography to actually verify the transaction. So the way that works is, let's say Alice owes Bob 5 Bitcoin. Alice has an address which produces a public key and a private key. And these two keys are actually mathematically related to one another. So Alice writes her message. Alice pays Bob 5 Bitcoin. And she uses her private key to sort of sign off on this message. And the way that works is this message is concatenated with the private key and the resulting string is hashed. This hash is then packaged with the original decrypted message along with the public key and passed on to a computer to be verified. The way the computer verifies it is by taking this public key and decrypting this original hash, and it should be able to match with the original decrypted message. If so, it's obviously a valid transaction, and Bob will eventually get his 5 Bitcoin. The way we traditionally view transactions as working is if I owe someone X amount of dollars, X dollars is subtracted from my account and added in the recipient's account. But that's not the best way to visualize Bitcoin transactions. Rather, you should let's think of Bitcoin's transactions like this. For example, if I have 4 Bitcoin and I owe someone 1 Bitcoin, my 4 Bitcoin is passed in through the transaction pool, and the recipient gets his 1 Bitcoin as an output. But I, as the payer, also become a recipient, and I get 3 Bitcoin as an output as well as change. And while this is unusual, this sort of way of thinking offers several benefits. If I wanted to calculate the current balance of someone's address in the older version, I would have to go back and look at every previous transaction and add up all the net gains and net losses to determine the average balance, the actual balance, which can be computationally intensive given the size of the graph. Whereas in this new model, I only have to look at outputs that are not inputs to newer transactions, outputs that don't point to anything else. And by adding these up, I eventually just add up all the net gains and get the actual balance, which ends up being a far more computationally efficient process. So once this transaction is set to be verified, it is sent to a pool of unverified transactions. Now, this network of computers that I mentioned before, or we also call them miners, take turns taking these unverified transactions, compiling them into a block, and offering this block to the blockchain to be added. The reason why I say offered is that the blockchain will only add a new block if the block is valid. And what I mean by that is the blockchain defines, for every successive block, the blockchain defines something as a sort of target or a sort of difficulty. A new block is valid if and only if the block's hash is smaller than this target value. So think of a block as a list of transactions along with another set of attributes. And these attributes may include the previous block hash, the timestamp, the Merkle root, which is the sort of hash of the transactions, along with several other things. And what miners do is they keep on trying different numbers called nonces and hashing that along with the rest of these attributes to produce an overall block hash. And they try to see if they can produce a block hash that is smaller than the given target value. And if it is, the block is considered valid and added to the blockchain. Now, there does exist uncommon scenarios where two blocks are added to the blockchain that are both valid and at the exact same time. So the way the blockchain works is it honestly just picks one and sticks with it when the next block after that is added, with the fundamental rule that the longest chain in the blockchain is always the main chain. Thus, any extra branches are automatically invalidated. So, so the benefit of this is that, so this ends up being, I guess, a very hard math problem. And the reason why people call it a hard math problem is that the block hash is, or given a set of attributes, it's easy to calculate the block hash, but given a block hash, it's pretty much impossible to identify exactly what set of attributes created that hash without really trying every possible set of attributes. And this adds a layer of security that we refer to as proof of work. So let's talk about maybe some of the sort of adversarial examples that could happen. Let's say someone wants to double spend, one of our earlier situations that I mentioned before. Well, there are three scenarios in which this can happen. Let's say someone spends the same amount of Bitcoin on two different transactions around the same time. So both of these unverified transactions can end up in the same pool. Well, in that case, obviously the first one that is verified will be verified, but the second one will be considered invalidated because the blockchains have been considered to be used up. Now there's a case where these two transactions end up in two separate valid blocks. Very unlikely, but it's possible. In that case, since I told you already how blockchain deals with two simultaneous blocks, one of the blocks is guaranteed to be invalidated, and therefore the double spending is not allowed. So the final situation is if the double spender wants to negate one of his previous transactions in a past block. Well, in order to do this, let's say he alters the record in some sort of past block. Well, that block will change, that block's hash will end up changing. But not only that, every successive block's hash after that will change as well, because what I mentioned is one of the attributes that each block contains is the previous hash, the previous block's hash. So in order for a double spender to successfully alter the blockchain, he would not only have to change the block that he's interested in, but every successive block after that. In the same amount of time it takes the rest of the world to just produce the next block on the original main chain. So in other words, it's not looking too good for our double spender. But so this is what we call proof of work, and it adds that extra security of people and prevents people from manipulating and taking advantage of the system. So here's the data of blockchain. This is parsed on the left, and I wanted to talk about it through the lens of relational databases. So a pretty intuitive approach to looking at this data is by splitting the data up into three main tables: one for transaction data, one for block data, and one for address data. And while this may seem like a very straightforward approach, this system or this type of organization leads itself to, again, some pretty computationally intensive queries, even if the query itself might be a pretty straightforward one. For example, if I wanted to determine how many common recipients does address A have with address B, that requires a pretty expensive join between the address table and the transactions table. And given the size of the blockchain, it can take a huge amount of time to actually run. So the point I want to emphasize here is that blockchain lends itself to a very natural graph-like format. As you can see, even by the name blockchain, it's a pretty obvious, I guess, pretty obvious counterpart or pretty obvious partner. So unsurprisingly, there have been past attempts to put blockchain on a sort of graph database. So these are some of the reports that I wanted to talk about that I found while doing my research in my time at TigerGraph. And one of the reports used Neo4j, and this is around 2013. That's when the blockchain was around 100 gigs of data in size. And Neo4j ended up exploding this to around 600 gigs to actually store it in a graph-like format. And the user reported that it took about 60+ days of exporting, which is obviously pretty absurd. Another report ended up using a 400-core computer to parse just 80 gigs and had to use a 12-core virtual machine and a 64-gig RAM to analyze the resulting graph. So the point here is that it required pretty intense hardware as well as some amazing specs in order to just maintain the graph, as well as perform some basic analysis and queries. So because of this, there are entire companies that are based off putting blockchain on a graph database. One is Graph Blockchain, which uses Apache Cassandra. Another is GraphSense, which uses the Agents Graph engine. TigerGraph fits into this sort of niche because it is able to scale with the exponential size of blockchain. On the left, you can see the graph of the growth of blockchain since its inception in 2009. And it grows really, really fast. But the importance of this is that TigerGraph can still, because it can scale with the exponential size, it can still be able to perform complex queries even as its network increases in size. And it actually stays relatively lightweight. So given around 200 gigs of data, of blockchain data, TigerGraph will hold a pretty similar amount, and it won't explode it to the same degree that other graph queries like other graph databases like Neo4j does, which is obviously a massive benefit. The way I got my raw data was by using an application called Bitcoin Core. So what Bitcoin Core does is it downloads the raw data from a copy of the main chain and downloads the copy of the main chain locally. And inside each of these files are contained information of the blocks. So as I mentioned before, the blocks contain a list of transactions along with certain attributes of the blocks themselves. Each of these transactions contain transaction attributes along with a list of inputs, so the things that went into the transaction, and a list of outputs, the sort of things that came out of the transaction. So as you can see, it's pretty condensed data. Now with that, I formulated this following structure of the graph, where you can see it uses mainly 4 different nodes. The first node is the address node, then the output node, the transaction node, and the block node. So the block node obviously represents a block. And the reason why it points to itself in this case is it represents the idea that one block node points to another, the successive block node, which in turn points to another successive block node. And this helps formulate the entire blockchain itself. Then you have the transaction node, which represents the process of a transaction occurring, and that points back to the block that it belongs to. Now, you might notice that there is no input nodes, and actually the output node it points towards the transaction, and the transaction points back towards the output. And this is because all input nodes are actually just outputs from previous transaction. In other words, there can exist no input that is not already an output from a previous transaction. And therefore, to simplify the data and the way we represent it, we can just represent all inputs and outputs as just output nodes. And then you have the address node. So every output points towards an address node, which essentially contains the public key that the user used. So putting this all together, this is sort of how the graph ends up looking like, where you can see your main blockchain in the top right, and you can see the transactions that point towards it along with the inputs and the different output nodes that belong to each transaction, as well as the addresses that each output points back towards. And we'll see a lot of this when I showcase how it actually looks up on TigerGraph. Here's a basic architecture of the sort of pre-processing that I built at TigerGraph to pre-process data. Obviously, since the data was pretty dense, it took a bit of time to actually unload and package this pre-processed data in order to be ready for uploading into TigerGraph itself. But if you have any specific questions about how this architecture works, I'd be more than happy to explain it. So now let's talk about how the graph looks on TigerGraph. These are some quick specs about the demo machine that we're using. The hardware is, here are the specs for the AWS EC2 instance that we're using. And after pre-processing, the Bitcoin data size ends up being slightly under 600 gigs, and the loading time just takes slightly under 3 hours. While the graph is held on TigerGraph, it has a size of 262 gigs. And during the loading process, it uses around 200 gigs of RAM. And for more information, you can actually check out this GitHub link, which contains a lot more detailed, actually, I think give me 1 second to share it. Right here, okay. Right, so here's the GitHub where you can actually see we have more information, and if you're more interested, you can read into it as well as look at the code that we used. So let's actually get started on looking at blockchain on TigerGraph. So here's GraphStudio for those of you who don't know what it is yet. And this is basically the UI that is pretty user-friendly and allows users to create the schema and load the data and sort of visualize the graph and play with it and make queries. And it's really, really easy to use. So here you have the design schema, which looks very similar to the one I defined in my graph before for the graph structure, where you have the block, transaction node, output nodes, and address nodes. Here's where we map the data onto the graph itself. And here's where we actually load the data. And on the right, you can notice different counts for the sort of total number of vertices, total number of edges, and the counts for each of the vertex types and edge types that you can see here. So let's explore the graph. Let's start off with something simple to just showcase the blockchain itself. So here we have a single block node. And if we were to look at some of the block nodes that appear on the same chain, here I'm exploding it one by one. Obviously, since it's a single chain, you see the blocks grow on either ends of it. So let's do one more. Give me 1 second here. Okay, yeah, let's do one more here. Okay, so we have so here you can see that we have the overall blockchain. Obviously, this is a very, very, very small part of it, but the idea still holds. This is a chain of block nodes. So now let's look at something also pretty interesting, which shows what are contained with each of these block nodes. So here I exploded from the blocks each of the transaction node that it's part of, and you might notice that there's let me put this in a nicer format to see. But you might notice that these red nodes, first off, are the transaction nodes. But you might notice that there's very few transactions per block, and the reason is the blocks that I selected right now are from the beginning of I guess Bitcoin, so you don't really see that many transactions occurring. But if we were to look at blocks later down the line, you would see a vast number of transactions occurring. So each of these transactions contain their outputs, which are represented by the blue nodes. And again, you can see there's not that many outputs occurring here, but the idea still holds. This is still early Bitcoin, and that's why you don't see that many. And then each of these addresses point to these green nodes. Each of these outputs point towards these addresses, which represent the green node. So as you can imagine, though this is a very, very small part of the blockchain as a whole, it lends itself to a very graph-like format, and we can really utilize this. So actually, let's do that by looking at some pretty interesting, I guess, addresses and values. So here are some interesting addresses that I thought would be worth pointing out. So Satoshi Nakamoto, for those who don't know, is the conceiver of Bitcoin and blockchain. And no one really knows who this person is. We don't know if Satoshi is his real name. We don't know if it's a single entity. We don't know if it's a group of people backed by the government. There's a lot of conspiracies, but whatever the case, it kind of adds to the sort of mystique behind Bitcoin. But this is the address of Satoshi Nakamoto, given that this is the first ever address that appeared on the blockchain. And what a lot of people do is, even now, to sort of thank Satoshi for making this idea and putting it out to fruition, people actually still, to this day, send Bitcoin to this address. So I thought it'd be worth kind of showing how it actually ends up looking. So let's hide this for now. So let's show this address node. So here's Satoshi's thing. We can then check out the different. So as you can see, as I mentioned, you can see a lot of input edges, or not actually, sorry, a lot of outputs that are connected to this address, and that represents all of the different donations people have given to this address, along with some of the behaviors. But I guess a really cool aspect of this is that you can pretty much view this sort of behavior for any address, and it helps you understand the behavior of that address, which can be used for some very, very interesting, I guess, results. Another thing I want to talk about was the pizza transaction. So in 2010 or 2011, some person actually ended up paying around 10,000 Bitcoin to buy 2 large pizzas at a Pizza Hut. And this was super, super important because I think this was the first ever time that Bitcoin was used to purchase tangible goods. And at the time, obviously, 10,000 Bitcoin is around $30, but in today's money, I think it's around 80 million. So you can also consider it pretty important because it's the most ever expensive like pizzas. But yeah, I thought it'd be interesting to also showcase how this transaction looks like. And you can see the people who participated in, as well as how the outputs moved around in time. So we can look at that as well. So here we can put in the address. So here we see the address. Now we can see all the things all the participants of it. So give me a second here. Okay. Right. Right. Okay. So you can see the input node here, and you can see the transaction value was it was 10,000 Bitcoin times 100 million Satoshi. So the units for a lot of these transaction values are in Satoshi, which is just a very, I guess, a submarker to Bitcoin. Just think of the translation like 100 million Satoshi is 1 Bitcoin. So this number is in Satoshi, but it translates to 10,000 Bitcoin. So this is the input. And you can easily see the two output quantities here. One is around half of that, and the other is the other half of that. Along with this, you can see that the block that this transaction was a part of. So you can also see that this was in 2010. So as I mentioned before. Now, the interesting part that I wanted to mention was now you can see how these transactions, how these outputs have been used further on. So we can expand this, and we can see that, oh, this transaction is part of this, is connected to this address, which is probably some Pizza Hut address, but it's now connected to this as it's now an input to this next new transaction. So we can look at this and see that, oh, okay, this transaction was now paid towards this block and this output. So I guess the cool part is you can really see how Bitcoins travel through time, which again adds to the idea of analyzing behavior. So with that, we can have some pretty interesting queries. One is obviously get balance. So given an address, how much total Bitcoin does that person have? And that utilizes that idea that we only have to look at outputs that are not inputs for any other transaction. So let's look at, for example, how much Satoshi has right now. So going back, let's put in Satoshi's address, and you can see that he has quite a bit of Satoshi, or quite a bit of Bitcoin. He's a very, very rich man. So to extend this even further, I wrote a query that determines the top K richest addresses on Bitcoin. So let's look at the top 3, for example. While this is running, let's get back to, I want to talk about a pretty interesting application of sort of understanding behavior and looking at Bitcoin that even the government has used. So Silk Road, if you may or may not know, is Silk Road is a website on the dark web, which is used for pretty illicit purposes. So it's used for like selling drugs, selling weapons, and it was a big deal because at a certain point of time, the government thought there was around about $1 billion of revenue passing through the website. So they really wanted to crack down on this. And this is where the interesting application of blockchain de-anonymization comes in. So what a lot of people do on websites is, on public forums, is they make posts like these. So what you may notice is that you have the actual post, but in the signature, you notice that they post their public address. The problem with this is that it is recommended that for every transaction that people make, they make an entirely new address. And this is just to add to that layer of security. But in reality, a lot of people do not do this. Instead, and it's for reasons like these. So obviously, if people end up paying to this public address, this address is used for a large number of times. But another problem arises. Because this public address is on a forum that's connected to this user 98326, this public address is now not isolated from the identity of the user. Because on this forum now, this user probably has attached a full name along with an email and other personally identifiable information. So this is how a lot of blockchain de-anonymization actually occurs. And a lot of companies actually utilize this aspect by web scraping these sort of forums and trying to build the identity behind these public keys. So one report actually ended up doing this and actually posted sort of how the graph looks like for, I think, several thousand transactions, which you can see here. And you can notice different behaviors that occur. So in the bottom right, I don't know if you can see my mouse, but you see a single entity type cluster where you have a guy pretty much using the same address for everything, and he's either paying a lot of people, or receiving money from a lot of people. But what you end up getting is a sort of single node type behavior, and you can see these people probably have a large amount of influence. Another thing is on the left-hand side, you can see sort of communities where you have a cluster of people paying or making transactions a lot between once another, and it's not necessarily as sparse as the general public. And you might notice, it's kind of hard to see, but some of the lines are thicker on, like, for example, the large volume transactions. And the thicker the line here, what the graph did was, it means the larger the transaction. And what you can do with this is that you can connect this with the idea of a single entity. And the idea here is that if a single entity is making a large amount of transactions, that kind of does raise some behavior, like some questions about, what are they actually doing? So it's with combination of both of these things that the FBI was able to crack down on the Silk Road founder. So the story is that what the FBI noticed was that on the Silk Road website, in the early parts of it, there was this username called Altoids, which was, I guess, posting very, very early on Silk Road, but it disappeared later on. And what they also noticed is on these Bitcoin public forums, they also noticed the same username Altoid. And, in the signature, they're able to also, I guess, support evidence based off of seeing if any large volume transactions occurred or if it's a single entity. So in combination of all of this, they were able to, with high confidence, determine that Altoids was the sort of founder or some big proponent of Silk Road. And because Altoids was obviously connected to personally identifiable information because of the forum, they were able to find the founder. And now they catch him and arrest him, and now he serves life in prison. So I think, that's obviously a very, very cool way of looking how addresses can be tracked back to their original identity and looking at the behavior of addresses over time. So let's look at how the queries look. Okay, so you can see that the 3 richest addresses appeared. We can see them in like a node view. So you can see each of them have a large number of Bitcoin. I think, in fact, this one actually ends up having like 100,000 Bitcoin. So really large amounts. You can also see this in JSON format right here, and the public address that this is connected to. So I think some really cool applications. So going back, the blockchain is really time series data, where each block is just a frozen state in time. And because of this, we can use this to study the behavior of addresses over time, like I mentioned before. This can be used for what we've already done to determine black market addresses and identify, sketchy behavior on the blockchain network. But another interesting application that people have considered is sort of predicting the stock price of cryptocurrencies. There's an interesting law called Metcalfe's law, which states that the value of a network is proportional to the number of active users squared. And what research has shown is that Bitcoin prices and Ethereum prices have correlated really, really well with this law. So it'd be interesting to, now that we have an ability to study addresses over this large network because of TigerGraph's capabilities and sort of predict the address's behavior in the future, it'd be interesting to apply this with Metcalfe's law to sort of predict the stock price. And another interesting aside is that Metcalfe's law works really, really well with pretty much any type of network, even social network. It's been shown to work super well with predicting Facebook stock, just if you were interested. Finally, it would be really interesting to sort of host the public ledger of blockchain on TigerGraph in a sort of dynamic format where any real-time transaction would be directly updated. And what this would involve is sort of streaming the transaction data as soon as it occurred into the TigerGraph database. And one of the cleanest ways to do this is with a Kafka loader. So this is where I transition back to Emma to talk about Kafka loader integration.
Thank
Emma?
you. Thank you, Sai. Yeah, so let me continue and share my, all right. I actually need to go to a later slide. All right. Yeah, thank you. Sai, it was a really, really good introduction and overview of blockchain and Bitcoin. Like, I learned a lot through your presentation, and the demo is definitely like superb. Yeah, thank you. And to everyone who wants to recreate this whole demo, you can go to the GitHub page that we open source the process, how you can pre-process and how you can load and also recreate those in TigerGraph. And you can actually use a developer version of TigerGraph to visualize everything. So now I'm going to quickly talk about the new feature Kafka Loader, which is a new feature in TigerGraph 2.3. And this will help you to integrate the live streaming data of Bitcoin. And first, I want to talk about the benefits of the Kafka loader. So the Kafka loader is a native way of connecting the external Kafka cluster to sending data to TigerGraph cluster. And it really increases the data availability and making sure that we get to the business value of the data very quickly. And with the Kafka loader, you can load the streaming and batch data from users' Kafka server. Just to notice that this is an external Kafka cluster. As a user, you have to install the Kafka cluster yourself. And then we can configure that in TigerGraph so that you can stream the data through Kafka. And we made it native in the sense that it is consistent with our current GSQL file loading data syntax. And we also added the multi-graph support, meaning if you have different business units having access to different Kafka cluster, you can stream it into a different graph if you have a data privacy and separation of control in your business unit. Of course, we chose Kafka because it's a very popular pub/sub system, and there's a lot of benefits in Kafka itself. It is very scalable. It is a distributed streaming platform, and it already has the built-in fault tolerance into it. And in itself, Kafka cluster, external Kafka cluster is actually a separate cluster, which means it actually serves as a data buffer for the TigerGraph cluster. So, the data will be kind of stored in Kafka first, and it won't really just crash the TigerGraph engine. And, the Kafka ecosystem has a lot of sink connectors and source connectors. So it's very extensible, and definitely it can help you to speed up the data pipeline from many other data sources into TigerGraph. Just quickly, an overview of a Kafka and TigerGraph data pipeline. You can stream the data from, you can import the data from the streaming data sources or static data sources through Kafka. And then leveraging the Kafka loader feature of TigerGraph, you can have all the data in your TigerGraph cluster, and you can write the graph queries and algorithm and get into the real-time graph analytics and feeding into the applications that you're building on top of TigerGraph. And with respect to Bitcoin streaming data, so as Sai mentioned, Bitcoin data is growing every day, and pretty much every 10 minutes there's new Bitcoin data. And if you have an external Kafka cluster set up, you can leverage this feature to actually update the graph in real time. You just have to pre-process the Bitcoin live data and set up the Kafka cluster and feed into TigerGraph. And you can do analysis on top of this updated graph continuously. So it's a very cool feature that you can think about integrate into your Bitcoin visualization and analysis. All right, I just want to summarize what we talked about today. Sai introduced how to load the Bitcoin dataset into TigerGraph. It was very detailed, and you can also follow those steps in the GitHub page, which is on the summary page too, the TigerGraph/Bitcoin to TigerGraph. And Sai did a really cool demo visualizing the Bitcoin dataset in TigerGraph. We also explored some of the interesting addresses. So you can do that yourself when you recreate this demo. And I also just quickly mentioned that how you can do the live streaming of Bitcoin data into TigerGraph, and you can analyze the data very in a continuous way. And we actually covered how to use a Kafka loader in Graph Guru 12. So if you want, just listen to Graph Guru 12, episode 12, so you know how to use the Kafka loader. And again, version 2.3 is available now. I encourage everyone to download and try to load the Bitcoin data and analyze it yourself. You'll have a lot of fun. Okay, now let's get to the Q&A. Let's see. Any questions? You can send the questions through the Q&A box. All right. Now, I see one question here. So The question is asking, how long does the Bitcoin data pre-processing take? That is the part that converting from the .dat to the CSV file.
Yeah, I can take that. So the pre-processing takes, so from the .dat file to the CSV file takes around 8 hours, which is a vast improvement from a lot of other past attempts. And this is, just to be clear, this is separate from the loading time it takes from like the CSV file into TigerGraph, which is slightly under 3 hours. Obviously, this can be improved with using a Kafka loader, because there's some overlap in the time it takes to pre-process the data and then at the same time start loading it into the graph itself. So this sort of 11-hour section in total can definitely be reduced. But to answer the question succinctly, it takes slightly under 8 hours to pre-process the data as of February 2019.
Okay, thank you. Okay, now I see one. There's a Q&A here. Okay, have you tried to map Ethereum's data where blocks are way smaller on a graph? So I think we actually have done something similar, not exactly Ethereum's data, but some other, I think, Ripple's data set. And
actually, yeah, the structures are almost the same, but we haven't just tried to do it. But since, as you mentioned, the data set is smaller on a graph, I think there should not be a big problem. Actually, you can refer to our Bitcoin to TigerGraph implementation and try to design your own schema and load it to TigerGraph.
Yeah, so that was actually He-Ting, one of our lead engineer who helped Sai during his time at TigerGraph. So yeah, thank you, He-Ting, for answering that question. All right, the next question. Okay, so can I have an instance with a smaller memory to load the Bitcoin data? Okay, so I will answer that. So first of all, let's just go back to the slide with this spec. What we used was a EC2 R5 machine in this demo machine. So it has 768 gig memory, but we definitely kind of a little bit over provisioned it. And when we were loading, looking at the stats, it only takes about 200 gig to load the data, which means if you're just thinking about loading the data, you can use a machine of 250 gig. That's enough. If you're thinking about like more complex queries, then you need a little bit larger machines to accommodate the computation, the memory usage during the computation. Okay. Another question, is the Kafka loader externally set up? Yeah, I'll also take this question. So it is, so Kafka loader itself is a built-in feature of TigerGraph. However, when you are doing the whole pipeline, let's go to this slide. You will have to set up your own Kafka cluster. And then you go through the Kafka loader, loading data into TigerGraph. And what you have to do, if you look at our documentation for 2.3 or just look at our, watch our webinars from Graph Guru 12, you'll know that you have to specify 2 configuration files in TigerGraph so that it recognizes the Kafka, where the external Kafka cluster is and how the message are sent, the offset and all kinds of information relating to the Kafka message queue. All right. I think I've seen answered all the questions. And okay, let me go back. Just to remind everyone here, we also have Graph Guru Developer Office Hours. This is every Thursday at 11 a.m. Pacific. And if you sign up, and you will get to a Zoom conference room, and you can talk directly with our engineers every week. And during this office hour, you can get your GSQL query reviewed, and we'll also help you to look at the graph modeling and schema, whether it fits your use cases. So it's a very useful resources, and take advantage of it. It's every Thursday at 11 a.m. Pacific. And there's more information on our website. And of course, you can catch up on previous episodes of Graph Gurus on our website as well. As I mentioned in Graph Guru 12, we covered how to use Kafka Loader. Watch it, and I encourage you to download 2.3 version, developer version, and go to the Bitcoin open source GitHub page and recreate a demo and play with the Bitcoin data. It's very exciting. All right, more resources here. Developer portal, developer version, Guru scripts, and join our developer forum. You can submit a lot more questions there too. All right, thank you. Thank you, Sai, for joining us today. And thank you everyone for spending your time listening to our webinar. Have a good day. Bye.